Molecular orbital theory. Learning each and every point of molecular orbital theory with examples. Easy trick to remember order of molecular orbitals and energy level diagrams. Firstly, let me teach you that why we need to study molecular orbital theory. Well, we study molecular orbital theory due to the defects in valence bond theory. For instance, valence bond theory states that atomic orbitals overlap to form a molecule. For example, in case of hydrogen molecule, the 1s atomic orbital of one hydrogen atom and 1s atomic orbital of another hydrogen atom overlap to form a hydrogen molecule. But VBT does not explain the molecular orbital of hydrogen molecule. Secondly, valence bond theory does not explain the stability of a hydrogen molecule. Thirdly, valence bond theory does not explain the paramagnetic or diamagnetic effect of hydrogen molecule. Thus, due to these defects in valence bond theory, we study molecular orbital theory. Now, what is molecular orbital theory? Molecular orbital theory states that how a molecule would behave after its formation. I mean, molecular orbital theory teaches us about BBDSP, bond order, bond length, diamagnetic effect, stability, and paramagnetic effect. For example, consider hydrogen molecule H2 positive ion and H2 negative ion. Valence bond theory does not explain the stability of these three substances. It is molecular orbital theory which explain all these 5 properties of these 3 substances, which we will learn later in this lecture. Thus note it down my personal mnemonic BBDSP for molecular orbital theory. Also remember that molecular orbital theory does not explain the formation of a molecule, but it only explains the behavior of a molecule. Now let me teach you the postulates or main points of molecular orbital theory. The first point of molecular orbital theory states that atomic orbitals combine together to form a new orbital known as molecular orbital. For example, consider these 2 hydrogen atoms. We know that this hydrogen atom has 1s atomic orbital and this hydrogen atom has also 1s atomic orbital. Now these 2 atoms of hydrogen would react chemically to form hydrogen molecule. Similarly, these 2 atomic orbitals of hydrogen would overlap to form 2 molecular orbitals. Remember that when atomic orbitals overlap, they lose their identity and form molecular orbitals. Thus, the first point of molecular orbital theory explains the formation of molecular orbitals from atomic orbitals. The second point of MOT states that the number of molecular orbitals formed are equal to the number of atomic orbitals combined or overlapped. For example, if 2 atomic orbitals overlap, it will form 2 molecular orbitals. If 6 atomic orbitals overlap, it will form 6 molecular orbitals. Thus, the second point of MOT is about the total number of molecular orbitals formed from atomic orbitals. The third point of MOT states that only those atomic orbitals combine together to form molecular orbitals which have comparable energy. For example, consider 2 1s orbitals. These both atomic orbitals have the same energy. So these both atomic orbitals overlap to form 2 molecular orbitals of 1s. Remember that 1s atomic orbital and 2s atomic orbital do not combine or overlap to form a molecular orbital. It is because there is much energy gap between them. Although 1s and 2p orbital can overlap to form molecular orbitals, because there is less energy gap between them. Thus, the third point of MOT is about the energy gap and probability of overlapping of atomic orbitals. The fourth point of MOT states that when 2 atomic orbitals overlap, they form 2 molecular orbitals. One is bonding molecular orbital and another is anti-bonding molecular orbital. For example, consider these 2 atomic orbitals. When they overlap, they form 2 molecular orbitals. This is bonding molecular orbital and this is anti-bonding molecular orbital. Thus, the fourth point of MOT is about the two types of molecular orbitals, bonding molecular orbital and anti-bonding molecular orbital. The fifth point of MOT states that bonding molecular orbital has lower energy than anti-bonding molecular orbital. For example, the bonding molecular orbital is always placed below anti-bonding molecular orbital because bonding molecular orbital has lower energy and anti-bonding molecular orbital has higher energy. The sixth point of MOT states that axial overlapping of atomic orbitals form sigma bond and parallel overlapping of atomic orbitals form pi bond. The seventh point of MOT states that the bonding molecular orbitals are represented by sigma and pi, while the anti-bonding molecular orbitals are represented by star sigma and star pi. For example, in this case, bonding molecular orbitals are represented by either sigma or pi, while anti-bonding molecular orbitals are represented by either star sigma or star pi. Remember that the star on the sigma and pi shows the higher energy of anti-bonding molecular orbitals. Thus, noted down all these postulates are main points of molecular orbital theory. Now, as we learned in our previous slide that molecular orbital theory explains the behavior of a molecule, I mean BBDSP. To learn the behavior of a molecule, we must understand the electronic configuration of a molecule. For example, consider two atoms of fluorine. We know that the atomic number of fluorine is 9. Now I do the electronic configuration of fluorine atom. 1s can accommodate 2 electrons, 2s can accommodate 2 electrons, 2px can accommodate 2 electrons, 2py can accommodate 2 electrons, and 2pz can accommodate 1 electron. Similarly, in the case of this fluorine atom, 1s can accommodate 2 electrons, 2s can accommodate 2 electrons, 2px can accommodate 2 electrons, 2py can accommodate 2 electrons, and 2pz can accommodate 1 electron. We know that these two atoms of fluorine will react together chemically to form fluorine molecule F2. What about the molecular orbitals of fluorine molecule? Well, we have already learned about them in molecular orbital theory. 1s atomic orbital of this fluorine atom and 1s atomic orbital of this fluorine atom would overlap to form two molecular orbitals, 1s and 1s. We already learned that one molecular orbital would be bonding molecular orbital and another would be anti-bonding molecular orbital. Also, we put star on anti-bonding molecular orbital. So two atomic orbitals of fluorine overlap to form two molecular orbitals. 2 electrons is accommodated in bonding molecular orbital 1s and 2 electron is accommodated in anti-bonding molecular orbital star 1s. Similarly, 2s atomic orbitals will overlap to form 2s molecular orbitals. 2 electrons is placed in this bonding molecular orbital and 2 electrons is placed in this anti-bonding molecular orbital. 2px atomic orbitals overlap to form 2 molecular orbitals. 2py atomic orbitals overlap to form 2 molecular orbital and 2pz atomic orbitals overlap to form 2pz molecular orbitals. Thus, this is the electronic configuration of atom like fluorine and this is the electronic configuration of a molecule like fluorine molecule. Remember that in case of electronic configuration of atom, we write one time as 1s, 2s, 2px, etc. While in case of electronic configuration of a molecule, we write 2 times as 1s, 1s, 2s, 2s, 2px, 2px, etc. Therefore, noted down this important point because a lot of students do not understand it. Now let me teach you my personal trick of writing molecular orbitals of any molecule. Firstly, I write atomic orbitals as 1s, 2s, 2px, 2py and 2pz. 1s atomic orbitals form sigma bond, 2s atomic orbitals form sigma bond, 2px and 2py orbitals can form pi bond, and 2pz atomic orbitals form sigma bond. Now what about molecular orbitals? Well, listen carefully. I write 1s and 1s 2 times. I write 2s and 2s 2 times. I write 2px is equal to 2py, 2pz, and again 2px is equal to 2py, 2pz. So I write each orbital 2 times. We know that 1s forms sigma bond, so put sigma with both 1s and put the star on the second one. 2s forms sigma bond, so put sigma with both the 2s and put the star on the second one. 2px and 2py form pi bond, so put pi with the 2px and 2py. 2pz forms sigma bond, so put sigma with the 2pz. Thus this is the second time, so put star on them. Remember that I write 2px is equal to 2py because they both have the same energy. Hence this is the electronic configuration of molecular orbitals of any molecule. Now using this electronic configuration, we can arrange the electrons of any molecule. For example, consider oxygen molecule. The total electrons in oxygen molecule is 16. There are 2 electrons present in sigma 1s, 2 electrons in sigma star 1s, 2 electrons in sigma 2s, 2 electrons in sigma star 2s, 2 electrons in pi 2px, 2 electrons in pi 2py, 2 electrons in sigma 2pz, and the remaining 2 electrons are present in pi star 2px and pi star 2py each. This is the electronic configuration of oxygen molecule. So note it down. Here, let me teach you one famous exam question. Find the bond order, stability and magnetic nature of H2 molecule, H2 positive ion and H2 negative ion. Well, in case of H2 molecule, there are 2 electrons present in it. So I write sigma 1s and it can accommodate 2 electrons of the hydrogen molecule. Secondly, in case of H2 positive ion, there is only 1 electron. So I write sigma 1s and it can accommodate the 1 electron of H2 positive ion. Thirdly, in case of H2 negative ion, there are 3 electrons present in it. So I write sigma 1s which can accommodate 2 electrons. I write sigma star 1s which can accommodate the remaining electrons of H2 negative ion. Now listen carefully. Bonding order is equal to number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbital divided by 2. Note down that bonding order means the number of bonds present in a molecule. In case of H2 molecule, bond order is equal to the number of electrons in bonding molecular orbital is 2 minus 0 because there is no electron present in anti-bonding molecular orbital divided by 2. So the bonding order of H2 molecule is 1. In case of H2 positive ion, bonding order is equal to there is 1 electron in bonding molecular orbital and no electron present in anti-bonding orbital, so minus 0 divided by 2. So the bonding order of H2 positive ion is 0.5. In the case of H2 negative ion, bonding order is equal to there are 2 electrons present in bonding molecular orbital minus 1 electron is present in anti-bonding molecular orbital divided by 2. So the bond order of H2 negative ion is also 0.1. Note down that stability is directly proportional to bonding order. The higher the number of bonding order, the higher would be the stability of a molecule. So H2 molecule is more stable than H2 positive ion and H2 negative ion. But what about the stability order of H2 positive ion and H2 negative ion? Because they have the same bond order 0.5, 0.5. Well, if the bond order of 2 molecules are the same, we look at the number of electrons in anti-bonding molecular orbital. In case of H2 positive ion, there is no electron present in anti-bonding molecular orbital. While in case of H2 negative ion, There is one electron present in anti-bonding molecular orbital. So H2 positive ion is more stable than H2 negative ion. Thus the order of stability is H2 molecule, H2 positive ion and H2 negative ion. Hence hydrogen molecule is more stable than H2 positive ion and H2 positive ion is more stable than H2 negative ion. Now what about the magnetic nature of these molecules? Well, a molecule is paramagnetic if it has unpaired electrons, while a molecule is diamagnetic if it has paired electrons. Paramagnetic means that it is attracted by the magnet, while diamagnetic means that it is repelled by the magnet. In case of H2 molecule, it has paired electrons, so it is diamagnetic. In case of H2 positive ion, it has unpaired electrons, so it is paramagnetic. While in case of H2 negative ion, it has also unpaired electrons, so it is paramagnetic. Thus, molecular orbital theory successfully explains the bond order, stability, and magnetic effect of all these molecules. Finally, let me draw the energy level diagram. When two 1s atomic orbital overlap, they form one bonding molecular orbital, sigma 1s, and one anti-bonding molecular orbital, sigma star 1s. When two 2s atomic orbitals overlap, they form one bonding molecular orbital, sigma 2s, and one anti-bonding molecular orbital, sigma star 2s. When two 2px, 2py, 2pz atomic orbitals overlap, they form three bonding molecular orbitals, pi 2px, pi 2py, because they have the same energy. One sigma 2pz molecular orbital which has slightly higher energy than pi 2px and pi 2py, while they also form three anti-bonding molecular orbitals, pi star 2px, pi star 2py, and sigma star 2pz. Also remember that sigma 1s bonding molecular orbital has lowest energy. 1s atomic orbital has more energy than sigma 1s, while sigma star 1s anti-bonding molecular orbital has higher energy than 1s atomic orbital, while sigma star 1s anti-bonding molecular orbital has higher energy than 1s atomic orbital. So the order of energy increases as you move up and sigma star 2pz has the highest energy. Thus, using this diagram, we can easily draw the energy level diagram of any molecule. For example, consider two nitrogen atoms. We know that the atomic number of nitrogen is 7. So in case of this nitrogen atom, 2 electrons are present in 1s, 2 electrons in 2s, and the remaining 3 electrons are present each in 2px, 2py, and 2pz. Remember that these 3 electrons have the same spin. Similarly, in case of this nitrogen atom, 2 electrons are present in 1s, 2 electrons in 2s, and the remaining 3 electrons are present each in 2px, 2py, and 2pz, each having same spin. Now 2 atoms of nitrogen will react to form nitrogen molecule. We know that there are 14 electrons present in nitrogen molecule. So 2 electrons are present in sigma 1s, 2 electrons in sigma star 1s, 2 electrons in sigma 2s, 2 electrons in sigma star 2s, 2 electrons in pi 2px, 2 electrons in pi 2py, and 2 electrons in sigma 2pz. So this is the energy level diagram of nitrogen molecule.